All right, so let's get started. So in Physics 1, we learned a bunch of stuff, right? We learned about positions and velocities and accelerations and forces and energy and momentum and all that stuff, torque. But if you think back to it, everything that we learned in that course could be boiled down to a handful of units that ended up being used, right? We measured 3 primary dimensions in Physics 1. We measured lengths, where the SI unit was meters. We measured masses, where the SI unit is... hang on, I need to plug in my laptop before I freeze. All right, so we measured lengths, masses, where the SI unit is kilograms, and we measured time, where the SI unit is seconds. But everything else that we did was some combination of those 3 things, right? When we talked about velocity, what's velocity? It's how far you traveled divided by how long it took. So it's meters per second. When we talked about forces, right? What was a force? Well, a newton of force was the amount of force that you had to push with. Max, enough! It was the amount of force you had to push with. Maxwell! The amount of force you had to push with to make 1 kilogram accelerate by 1 meter per second Momentum was mass times velocity, kilograms times meters per second. So everything that we learned in Physics 1, everything, was some combination of lengths, masses, and times. So the big reveal in this course is that we introduce a 4th base unit to our repertoire, and that's the unit of electric charge. Could have had a cat. Could have had a cat. All right. So, this idea of electric charge. Right? It's just this fundamental property that matter has. Just like mass is a property that an object has, an object can have charge. And a lot of stuff about charge you guys already know because you learned it in grade school, right? I think I had some of this stuff taught to me by Big Bird on Sesame Street. That's how long ago you'll learn some of these concepts. But you've probably not had to think about these concepts in terms of the level of detail that we're going to deal with them this semester. That's where the new stuff's going to come from. So we know that electric charge has 2 types. We know that there's positive charge and negative charge. Right? Every grade school kid knows at least that much. We also know that electric charge exerts forces, right? You know that light charges repel.
Like magnets.
Very much like a magnet. It's not the same thing. We'll learn about magnets in chapter 22, but it's similar in that light repels and unlike charges attract. Again, everybody coming into this class already knows that. They just may not know the details of that repulsion or attraction. And that's what we're going to delve into. Now, what you probably don't know going into this course is how you measure electric charge. What unit are we going to use to quantify the amount of charge that something has?
And would you use joules or watts?
Well, no, because remember, a joule is a kilogram meter squared per second squared. And a watt is a joule per second. So it's a kilogram meter squared per second squared per second. So all of those things from last semester, they're just combinations of lengths, masses, and times. Charge is something new. It's an entirely new unit that we haven't seen before. And the unit that we're going to use to measure charge is called the Coulomb.
Oh, I remember that.
Yeah. This is a fourth base unit that we will introduce in chapter 18, and it's going to stick with us for literally the rest of the semester. We're going to talk about charge measured in coulombs. Now, before I get into the Coulomb force law and the nature of this attraction, there is another thing that I probably should deal with, and that's the concept of conservation of charge. So charge is conserved. So Kayla, do you remember what it means? Not conversed, geez. Conserved. I'm getting dyslexic in my old age. What do I mean when I say that something is conserved?
I remember it when it would equal to 0. It didn't go. It didn't do more. It like. It was like, I remember the path and how it stayed on a path, like the total work done.
Yeah, you're thinking about conservative forces, which is it's in the right bailiwick. But conservation, when you say an item is conserved, what we mean is that the total amount of whatever that stuff is doesn't change. And so when we talked about energy last semester. As long as you only had conservative forces where the total work over a path was always 0, then the amount of energy that you had was conserved. Because what would happen is, if I have an object in one location and I move it to some other location, well, as I move from here to here, the potential energy might change. The potential energy might go up. But however much the potential energy goes up, the kinetic energy would go down by the same amount. So the total energy I had never changed. The one went up, the other went down, but the total amount of energy that I had in everything stayed constant. And that's what it means to say that something is conserved. Max, enough, buddy, he's gone. So, hang on. Maxwell, I'm going to murder you. Here. Come here. Here. Come here. Daddy's working. Leave me alone. Come here. This is the worst dog ever. All right. So, when we say that charge is conserved, we mean the total amount of charge something has remains constant. And to give you a sense of how that is, let me switch screen shares for a moment. And I'll go to here. So here's a sweater and a balloon. And what we know is that all matter, everything, is constructed of atoms, right? And what are atoms constructed out of? Well, they have positively charged nuclei surrounded by a cloud of electrons that are negatively charged. So, this sweater has a charge of 0, because if I were to zoom in and actually look at individual atoms, what I would see is that for every positively charged nucleus of an atom in this sweater, there is a similar amount of negative charge orbiting around, and as a consequence, the total charge of the sweater is 0. Right? That's pretty straightforward.
Mm-hmm.
Now, I also know that if I were to take this balloon and rub that balloon up against the sweater, then what could happen is I may acquire a certain amount of static electricity, right? If you've ever, rubbed a balloon and stuck it on the wall, you've certainly experienced that same sort of process. Now, what's happening when I do that? Well, when I take this balloon and I rub it against the sweater, what's happening is the friction between the two objects tends to rip electrons off of the atoms in the sweater, And as a consequence, the balloon ends up with more negative charge than it originally had. But the sweater, by comparison, ends up with a whole bunch of atoms that have fewer electrons than they're supposed to. Make sense?
Mm-hmm.
Notice, however, that for every electron the sweater lost, the balloon picked one up. So the total charge is still going to be 0, right? You had 0 charge for both of them before, and now if I just show the charge differences, what you'll see is that if I were to count all of those pluses, the positive charges that remain on the sweater, and count all the negative charges that I have on the balloon, that number will still total up to 0. All the pluses are canceled out by all the negatives. They're just in different locations. So that's what we mean. We say that charge is conserved. I can't put negative charge on the balloon without removing some negative charge from the sweater so that the total will remain 0.
Okay.
That's the idea. So, thank you, Val. Appreciate you showing up. All right. So that's what I mean when I talk about conservation of charge, the idea that charge is conserved. And the idea is simple, that electrons don't just vanish. Protons can't just be annihilated. They will always exist. All right, you be quiet now? Thank you. No, he's not going to be quiet now because he's a jerk. Could have had a cat. All right, so that's the idea, that charge is conserved. So at this point, let's drill down into the specifics of how this force works. We know that these charges repel each other, they attract each other. What we don't know is how or to what extent. And that is where we will use something called the Coulomb force law. And that says that the force between two charges is given by the following expression. Now, obviously F is the force that the two charges are going to feel. And in these expressions, when you see the letter Q, you're going to start to learn to associate the letter Q with charge. Q always means charge. So Q1 and Q2 are the amount of charge of the two objects in question. And I should point out this specifically only works for point charges.
It only works for what?
For point charges. Where all the charge is isolated to a very specific location. Think back to that example where I was talking about the sweater and the balloon, right? I might use the charge on the sweater as Q1 and the charge on the balloon as Q2, but what's going to happen is that charge in the sweater was literally localized all along the sleeve, and the charge on the balloon was localized all along one side of the balloon. And the reason that matters is because the R in this expression is the distance from one charge to the other. And so if I tried to use this Coulomb force law for the balloon, what's going to happen is, like, if I ask you how far is the charge on the sweater from the charge on the balloon, that's a somewhat difficult to answer question, because, you know, if you look at the charges that are at the top of the sleeve, they're further away than the charges in the middle of the sleeve. Does that make sense?
Yes.
So that's why we don't use this for extended objects. We use it specifically for point charges. If I wanted to solve the problem of the force between the sweater and the balloon, I'd have to use calculus, right? To deal with the fact that each little piece of charge has a different distance from each other piece of charge. So specifically, this is only good for point charges. But we would use calculus in combination with this to do something more complicated. But that's beyond the scope of this class. So the good news for you is that we're almost always going to be talking about point charges, because if I don't do point charges, the math is more complicated than we're going to deal with. So that's the two charges. This is the distance between the charges. A lot of times people see R and they naturally think radius, but you should get out of that habit because that can get you into trouble.
And would K be the electrostatic constant?
Yep. It's the electrostatic, or sometimes called the Coulomb constant. And it's just a number, the specific value of which is 8.99 times 10 to the ninth, and it has units of Newton meters squared per Coulomb squared. And you can see that it has to be those units, because in order for me to get a force that comes out in newtons, I'll take K, which has these units, I'll multiply it by two charges, so those are in coulombs, which means that'll cancel the coulombs on the bottom. I'll divide it by a distance in meters squared, that'll cancel the meter squared on the top. So when these cancel out, it leaves behind newtons, which is what I'm supposed to have. Now, that's important because it means that when I use the Coulomb force law, I have to be consistent. Since K has these units baked in, you have to use the same units for Q and R. So anytime I'm using the Coulomb force law, all of my charges need to be specified in terms of coulombs, and all of my distances need to be specified in terms of meters, not centimeters or kilometers or anything crazy like that. Now, that's often an issue because a coulomb of charge is an enormous amount of charge, right?
Mm-hmm.
You don't usually see an entire coulomb just sitting around someplace. And so it's not going to be uncommon for charges in a problem to be specified in microcoulombs or even nano or picocoulombs. So make sure you make those conversions, and if you're not already up to speed, you're going to want to make sure that you know all those metric prefixes. The ones like milli, you mostly already know. That means 1,000th or 10 to the minus 3. But there's also micro, and of course, micro is given by the Greek letter mu as the prefix, whereas milli is just lowercase m. Micro is 10 to the negative 6th. Sometimes you'll see nano, that's just n, 10 to the negative 9. And even pico, which is lowercase p, that's 10 to the negative 12. So 1 picocoulomb is 1/1,000,000th of a coulomb. So make sure you bone up on those because you guys are science majors and I expect you to know the metric system. One thing I'll point out is that in addition to charge being conserved, charge is also quantized. Let's go back to that other sheet for a second. What do I mean when I say that something is quantized?
Mm.
Don't know that term?
No.
All right. You probably saw it when you took general chemistry, because what you learn in general chemistry is that the energy of an electron in an atom is quantized. That's probably where you first see that term. And when we say that something is quantized, we mean that it comes in discrete units. In other words, I could have 1 unit or 2 units or 3 units, but I couldn't have 1.5 units or 1.7 units, right? They come in whole chunks, right? Money is quantized. if I owe you money, I can't pay you half a cent. That doesn't happen, right? Because we only make denominations of money that come in units of pennies, right? So we would say that a penny is one quanta of money. You can't have fractions smaller than that. That's the smallest increment that they come in. People have talked for years about not making pennies anymore, right? If they did, then the quanta of money would change to be a nickel. And you wouldn't be able to have any increment of money that was smaller than 5 cents. Does that make sense?
Yeah.
That's the idea. So what's going to happen is the quanta of charge is the charge of an electron or a proton. You never are going to see a charge in an increment that's smaller than that. Assuming we don't talk about quarks, which we're not gonna because they're outside the scope of this class. So for all intents and purposes, you can't get less charge than the charge of a single electron. So how many coulombs is the charge of one electron or one proton? Well, it turns out that one electron has a charge of about 1.602 times 10 to the negative 19th coulombs. So this is one quanta of charge. And of course, protons are the same number. Of course, electrons are negative charge, so I should make it negative. And one proton is the same amount of charge And what's going to happen is, since this number is so dinky, if I have 5 microcoulombs, that's a super tiny number of coulombs. But 5 microcoulombs is still going to end up being, like in the tens of billions of electrons. So usually we don't worry about the quantization for the most part, but we do know at the bottom that it's there. We call this number the elementary charge. And it's sometimes denoted with the lowercase letter e. So when you see that lowercase letter e, we're talking about the charge of a single electron or a single proton.
Okay.
Yeah. Some of your homework problems, you have to use that. There's a couple homework problems where I ask you to figure out things like, hey, I've got a ball that's got 5 microcoulombs of charge on it. How many electrons is that? Well, you know that each electron has an elementary charge, so you can figure it out. All right. So we've got all the major pieces in place. We've got this Coulomb force law, and all that remains is that we learn how to utilize it. So let's imagine I've got the following example. I've got positive charge and a negative charge. They're both point charges. Let's say that this guy over here is 10 microcoulombs, and this guy over here is 5 microcoulombs, but this one's negative. And I ask you to find max enough. Actually, let's change something just so that I illustrate an important point. Let's make this positive and negative. If I do the other way, I might inadvertently reinforce a common misconception, and I want to make sure I don't do that. So what force am I going to experience in this problem? Well, I know I'm going to use the Coulomb force law, which is K, Q1, Q2 over R squared. Let's have these guys be 20 centimeters apart. And so I go to figure this out. And it's just a matter of plugging in numbers. So K is 8.99 times 10 to the positive ninth. Q, I have to convert into coulombs because I have it specified in microcoulombs. But I know that 10 to the minus 6 means micro, so I can go 10 times 10 to the negative 6 coulombs. And here's where something important happens. The Coulomb force law tells me the magnitude of the force. Remember, vectors have both a magnitude and a direction. And right now, I don't care about the direction. I'll worry about that in a minute. Right now, I care about the magnitude. And by definition, magnitudes are always positive. Now, what that means in practical terms for us is that when I'm using the Coulomb force law, even if I have a negative charge, I'm not going to plug a negative number into that formula. And in fact, a lot of textbooks will go so far when they write the Coulomb force law as to put absolute value symbols around Q, right? But I see students sometimes, they'll plug minus signs into the equation, and that can get you into trouble. So never plug a minus sign into the Coulomb force law. Just realize that when you get your numbers out, you're going to get a positive answer, but then you're going to have to look at that positive answer and use some common sense to decide whether you want that direction to be positive or negative. And that's going to depend on your coordinate system. So far, so good?
Yes.
All right. So meanwhile, I got K. This is Q1. Q2 is this guy. And then, of course, I'm going to put this over r squared. However, my distance I specified in centimeters, so I have to convert that into meters, and I know that 20 centimeters is the same as 0.2 meters. I'm dividing by 100. And now I could go in and crunch those numbers. And of course, I pick numbers that I can't do in my head because such is life. All right, so crunching those numbers real quick, I get, we'll call it 11.24. All right, so that's the magnitude of the force exerted on the negative charge. What direction is that force?
In the positive.
Well, hang on a second. We talk about the direction and whether that direction is positive or negative. That depends on the coordinate system that we've chosen, right? Mm-hmm. We haven't talked about that yet. What coordinate system should I use? Well, unless I have a compelling reason not to, I almost always choose kind of your basic boring Cartesian coordinate system, where the x direction is probably positive to the right, and the y direction is probably positive going up and down. So if I have a negative force, that force would be to the left, and if I had a positive force, that force would be to the right. So is this force to the left, or is it to the right?
To the right.
Yeah, because I'm finding the force felt by the negative charge, right? Mm-hmm. This negative charge would be attracted to that positive charge. So this guy would get pulled to the right. So I definitely want that to be something positive. I'd call that 11.24 I hat if you wanted to put it in vector notation. But it would definitely be positive. Right? And I did that as an example because you'll notice in this case here, even though this is the negative charge, it had a force in the positive direction. That was completely arbitrary. Now, the third law of motion from last semester says that if this guy is being pulled to the right with this many newtons, the positive charge, by the comparison, is being pulled the opposite direction with the same force. That's Newton's third law. So had I asked you for the force on the positive charge, it would have been the exact same number, but it would have been to the left. Does that make sense?
Can you say that one more time?
So if the negative charge here, that negative 10 microcoulombs, is getting pulled to the right with 11.24 newtons of force, mm-hmm. Newton's third law says that the pusher feels the same force as the pushee, but in the opposite direction.
Okay.
So that suggests that this guy is feeling the exact same size force, but it's to the left. Does that make sense?
Yeah.
So, which one is the positive direction, which one is the negative direction? That depended completely on how I defined my coordinate system. But even if I redefine my coordinate system, what would always be true is that these two guys would feel forces in opposite directions. This one to the right, that one to the left. Right, super easy. We can do this all day. How are we doing?
Good. Were you talking to me or the dog?
You. The dog is strangely silent. I'm somewhat surprised. All right, so that's all fine and dandy. So obviously you know what's going to happen next. We're going to make it more complicated. Right? How can I make it more complicated? Well, what if I have the exact same problem? Here's 10 microcoulombs. Here's positive 5 microcoulombs. That's 20 centimeters. Let's just add a third charge.
Do we have to make a triangle with this?
Possibly. It's going to depend on the geometry of your problem. So let's do this two different ways. First thing I want to do is I want to figure out the magnitude and direction of the force felt by the upper left charge. Right. We'll do this one first because it's easier. So, when I'm doing this, I'm just going to rely on the fact that the Coulomb force law obeys something called the principle of superposition, which is a fancy schmancy way of saying that forces add up because they're vectors, right? But you have to add them like vectors. So if I want to find the force experienced by this charge here, what I'm going to do is I'm going to figure out what force this guy feels because of this guy separately from what force this guy feels because of this guy. Then once I know what those two forces are, then I'll add them up like vectors. So far, so good?
Yes.
Now, the good news for us is we've already solved the first part. We already know that this guy is going to feel a force towards this guy of 11.24 newtons. It's the thing we got a minute ago, right? Mm-hmm. So he's going to feel two forces. I'm going to draw a free body diagram off to the side. I'm going to call F1 the force he feels because of this guy. And we already know that's 11.24 newtons. I'm trying to write too small. That's probably illegible. You guys with me on that?
I have a question real quick.
Huh?
When you say how the 10 always goes to the 5. Are they both coming together at the same, or is the 5 just stationary and then the 10?
Well, so right now, if those were the only forces acting on them, if this guy had a 11 Newton force acting on it, it would for sure get pulled to the right. It would end up moving. And this guy over here, if he had a force pulling him to the left and no other forces, then he would also end up moving. So if those were the only forces in town, they would come together and crash somewhere in the middle, right?
Okay.
But right now I'm not even worried about them moving. I'm kind of taking a snapshot of what their forces are at that one moment. And it may be that there are other forces. Maybe this guy is nailed to the wall and he can't move, right? So maybe there's forces from the pin holding him in place, and I don't care about those. So the answer to your question is maybe, depending on the situation. But right now, I'm not super worried about the dynamics of the system. I'm not worried about what happens as time progresses. I'm worried more about the statics. At this one moment in time, how hard are they being pulled? So I'm not going to give them a chance.
24 newtons.
What's that?
The force one is 11.24 newtons.
Correct. We already solved that problem. So we know that answer already. So part of why I'm choosing this example is because I can do it quickly because we've already done half the work. So far, so good?
This may seem dumb, but wouldn't they repel from each other since they're
Yes,
both
they will, and I'm glad you got that, because that's where we're going next, right? We have an F2. That's going to be the force that this guy feels because of this guy. And you're correct. These are both negative, which means they're going to repel each other. So this guy is going to get pushed in what direction?
Up.
Upward. Awesome. So F2, I already know, is going to be upward. How big is F2 going to be? If you're clever, you do it in your head.
Wouldn't it be 0?
Nope. So here's what I'm going to do. If I wanted to figure it out, I would use the Coulomb force law. Mm-hmm. It's going to be K times Q1 times Q2 divided by R squared, right? Now, I already know that when I use this Q and this R, I get 11.24, right?
Okay.
Now, what changed? Well, instead of having 10 and 5 as my two Qs, I have 10 and 10.
Oh, isn't it gonna be K? What K is?
Well, K hasn't changed, right? So I'm taking the same K that we had before, and I'm multiplying by one of the same Qs as I had before, but the new Q for Q2 is twice as big as the old Q2. So just making this Q2 be twice as big, that's going to tend to make my answer twice as large. So if all I was doing was changing the Qs, I would have double that, which would be, double that's going to be 11.48. Or 22.48, excuse me. But that's not the whole story.
Because the distance is also cut in half.
I'm sorry, what?
Isn't the distance is cut in half?
Yes. So what effect does cutting the distance in half have on my force? Is making the distance half as big going to make my force larger or smaller?
Smaller. No, larger.
Yes, because I'm dividing by less, right?
Yeah.
Except the R is squared. So when I cut the distance in half, my denominator is not going to be half as big as it used to be, because that would double my force. It's going to be 4 times smaller. It's going to quadruple my force. Does that make sense?
A little bit.
I put that kind of proportional reasoning stuff on your quizzes all the time. Right? You've answered a gazillion questions like this before. So like if I make the bottom twice as big, but then I square it, the bottom would be 4 times bigger. And if I divide by 4 times bigger, it would cut my thing in fourths. If I make my thing half as big, well, 1/2 squared is 1/4. But if I make the bottom 1/4 as big, that makes my answer 4 times larger. So in my head, I can do this super easily. Doubling Q is going to double my answer. Halving this is going to quadruple my answer. So a half times a quadruple is 8. So this force is going to be 8 times the old force. So super lazy, take 11.24 times 8. I get 89.9. And I could plug in, 8.99 times 10 to the 9th, and I could plug in 10 times 10 to the minus 6 and 10 times 10 to the minus 6 and 0.1 squared and do all that math. I'm going to get this. Does that make sense?
Yeah.
So awesome. Now I know that this guy feels 2 forces, an 89.9 Newton force upward and a 11.24 Newton force to the right. How do I find the magnitude and direction of that force?
I want to say you would do you would use sine and cosine since it's in triangle format, but
Sort of. Well, let's take this and write our answer in vector notation, right? So what we know is that my total force F is going to be this much, 11.24 I hat, because that's the sideways part, plus 89.9 J hat. So this represents my final answer. But how do I even visualize that? Well, if I have a vector that's 11.24 I hat, it means it's sideways 11.24 newtons. But it's upward 89.9 newtons. Obviously, this picture is not to scale, right?
mm-hmm.
The total magnitude is the vector that goes from the tail of the first to the tip of the last. So this right here, this diagonal vector, is my final answer. In other words, this guy here is being pushed up and to the right. How much force is he being pushed with? This much force. But that means I need to figure out how long that vector is. So how do I find the length of that vector? That's a right triangle.
Yeah, a squared plus b squared equals c squared.
Exactly. I'll use the Pythagorean theorem. So what's going to happen is the two components that I got are just the sides of that vector. So my magnitude of F is going to be the square root of 11.24 squared plus 89.9 squared. And that's a number that I can easily crunch. Oops. Let's square root that. And I get 90.6. So far, so good?
Yes.
Now, you'll notice I asked you for two things. I asked you for the magnitude, which is clearly that. But I also asked you about the direction. And I can specify the direction in a very vague way by saying that clearly it's up and to the right. But up and to the right is very vague. It's not very specific, you know. Any number of diagonals can be up and to the right. So if I want to specify it more exactly, I probably have to specify it in terms of what angle it makes with the horizontal. So here's the angle that it makes with the horizontal. What angle is that?
I would say 45 degrees just by looking at it, but
It can't be 45 degrees because a 45-degree triangle would be isosceles, right? The x and the y parts would be equally long. Remember, this drawing is not to scale. It looks like to scale it might be 45 degrees, but in reality, this side of the triangle is like way longer than that side of the triangle. So just looking at it and knowing that this is way longer than this, that angle is going to have to be way bigger than 45 degrees. So it's got a short sideways part and a super long vertical part. It's got to be super steep. It doesn't look that way in the picture because I didn't draw it to scale. But to figure out what that angle would be, I could use SOHCAHTOA. And I know that the tangent of whatever that angle is should be the ratio of the opposite side over the adjacent side. So if I take the inverse tangent of that ratio, that'll give me my actual angle. So 89.9 divided by 11.24. Take the inverse tangent of that, and I get a whopping 82.9 degrees. Which, as I suspected, is way bigger than 45. So sometimes when you want to specify the direction, you're going to look at how the two components compare to each other, and that ratio is going to end up telling you the angle. Super easy, right?
Mm-hmm.
Let's make it more complicated. Let's take the exact same picture, except I want to find the force acting on one of the other charges. Let's find the force felt by the positive charge. I want to find the force felt by this guy over here. What's different?
It's positive.
Okay.
So the number is smaller. Well, the 5 is smaller.
Aha! So that's certainly true. So if I want to go about this, I'll do the same trick for this charge that I did for this charge, right?
Mm-hmm.
This guy felt one force to the right from him and one force upward from him. Now, what about this guy? If I do the free body diagram for this guy, what direction force is it going to feel from this guy?
It's going to go to the left.
Yeah. So he's going to feel, for him, his, we'll call it F1, is to the left. What about F2? What force does this guy feel because of this guy?
He's not going, he's on a slant.
Yeah.
He's going towards, I was going to say downwards, but that's technically right. He's going towards the -10.
That's exactly right. So what's more complicated about this one, the reason we're doing this example second, is because this guy here is going to feel a diagonal force from this guy here. It's going to be attractive, so it's going to be along a line that goes straight between the two, but it's going to be annoying and diagonal. So we're going to still have to add two vectors, but one of those vectors is going to be annoying and diagonal. So let's do the math. And again, what's going to be easy for us is we already know F1, because F1 is 11.24 still, because
they're the same.
Yeah, they're the same. Whatever force this guy felt to the right, this guy's going to feel that same force, but to the left. So F1 we already know, it's going to be 11.24 I hat. However, because it's to the left, slapping a minus sign on it. You with me?
Yes.
Awesome. So we've got F1. F2 is trickier. And F2 we're going to have to do a little thinking. So F2 we're going to get by doing K, Q1, Q2 over R squared. So 8.99 times 10 to the 9th. Q1 is going to be 5 microcoulombs, so 5 times 10 to the minus 6. And Q2 is 10 times 10 to the minus 6. So far, so good? You with me on that?
Mm-hmm.
I'm using this charge for Q1 and that charge for Q2. All right, well, wait a second. What the heck is R?
Can't you...
Back to the picture there. What
Can't
is...
you do A squared plus B squared equals C squared?
Exactly, because what's going to happen is I have to look at the picture here, and R is the distance straight from here to there, which is not 20, it's bigger than 20, it's not 10, it's bigger than 10. It's going to be the hypotenuse of this right triangle. So in a lot of these point charge problems, R is going to be one of those things that you may not necessarily know up front. They may not just flat out tell you R, but they'll always give you enough information to figure it out by using the geometry of the problem. And in this case here, the way we would do that is with the Pythagorean theorem. So R would be the square root of 0.1 squared, that's this distance, plus 0.2 squared. And the cool part is that on the bottom here, I have R squared, right?
Mm-hmm.
So 0.1 squared plus 0.2 squared, square rooted, but then squared, the square root part just cancels. And I just put it in like that. So now I'm crunching numbers, 8.99 times 10 to the 9th times 5 times 10 to the minus 6 times 10 times 10 to the minus 6 divided by And I'm going to have 0.1 squared plus 0.2 squared. Oops, I made a typo. Oh gosh. Now I have made multiple typos. Let's start over. Did you get an answer?
I got 8.99.
That is because that is the correct answer. Good job. So, this is the magnitude of F2. However, in order for me to add F1 and F2, I have to have them in component form, right?
Mm-hmm.
F1 was easy to get in component form because it was straight up to the left. But F2 is not so easy because it's 8.99 diagonally. So in order for me to break that down into components, I'm going to have to break that 8.99 down into some kind of X and Y components. So visually, I know that this is 8.99. I got to find the X part. I got to find the Y part. And it's going to make some kind of angle with the horizontal. And I don't know what that angle is. So how am I going to figure this angle out?
Can't you do what we did last time?
Yeah, it helps to go back to the original picture. And you'll notice that the angle that F2 makes is the same as this angle right here, right? Which means this triangle here is similar to this triangle here. So what I can do is go back to this triangle and say, aha, I'm looking for this angle there. And I can use SOHCAHTOA, except that for this triangle, I know that this is 10 centimeters, that's 20 centimeters, this is however many centimeters that is. I know all three sides. And so I could figure out what that angle is. I could say that the tangent of that angle is opposite, that's 0.1, over adjacent, 0.2, right?
Mm-hmm.
And then take the inverse tangent of 2, and I get that it's 63.4 degrees. So now I know this angle is 63.4 degrees, and I can use that to find the X and the Y components. So F2 is going to be 8.99 times the cosine of 63.4 degrees in the I-hat direction, plus 8.99 times the sine of 63.4 degrees in the J-hat direction. Except I've made an error. Do you see it?
Are you supposed to reverse sine and cosine?
No, not that, not that. This force is to the left and down, right?
Mm-hmm.
So the I-hat part is negative because it's to the left, and the J-hat part is negative because it's down. So I had to make them both negative.
Okay.
Yeah. I know that I have the X part is the adjacent part of the triangle. That's why it's the cosine. It's SOHCAHTOA. And the Y part is the opposite side of the triangle. That's why it's the sine, because sine is opposite over hypotenuse. So I got the cosines and the sines in the right place. I just did not reverse the sines. Whew. So now what's happened is I've taken my two vectors. I've broken F1 into its vector components. It's got a negative I-hat and a 0 J-hat. This one has I-hat and J-hat components. Now what I can do is find F total and just add them all up. So when I add this to this, well, to get the I hat part, I'm going to take 11.24 negative plus this number here. That's going to be the I hat part of my answer. So let's crunch that number real quick. So if I take 8.99 times the cosine of 63.4, so this number right here is 4.02. So together, this plus this is going to be negative 15.26.
Okay, that's what I got.
Right? That's the I hat component of my final answer. And then this is 0 plus this.
You just bring that down.
Yep.
Right.
So 8.99 times the sine of 63.4 is negative 8.03 is what I'm getting. So far, so good?
Yes.
So, all that's going to happen is the total force experienced by that 5 microcoulomb force, it's going to be down and to the left. So it's this much left and this much down. But if I wanted to find the magnitude and direction, I wouldn't want to cite my answer like this, because I can visualize that this is going to be a vector that's to the left, 15.26. It's down 8.03. So my final answer is down and to the left this much. To find that magnitude, I would do the square root of 15.26 squared plus 8.03 squared. So 8.03 squared plus, what was the other one?
I got 17.24.
All right, that seems reasonable. Yep, awesome. So we know that it's going to feel a force of 17.24 newtons. Oh, I don't want to check my mail. Go away. And what direction is it? It's down and to the left, but I'd probably specify with an angle. How would I get that angle? Opposite over adjacent. So the tangent of my final answer is going to be 8.03 divided by 15.26. So therefore, theta equals what? The inverse tangent of... I get 27.75 degrees. So I can say that it's in a direction down and to the left at an angle of 27.75 degrees below the horizontal.
Okay.
Super easy, right?
Yeah.
That's it. That's all there is to it. To do the Coulomb force law, you have to be able to identify the R's in question. You have to be able to break things down into components appropriately. Super, super easy. Let's do one more little bit of example before we move on to bigger and better things. So far, so good?
Mm-hmm.
All right. So what I want to do now is I want to take this new thing that we've learned, this new force that we've learned about, and I want to apply it to the same kinds of problems we did last semester, right? Because at the end of the day, the Coulomb force is just another force, and it obeys all the same stupid rules as all those other forces. So I want to do a Newton's law problem, like from chapter 4, except now we know about more forces than we used to know. So here's the scenario. all right, I'm going to take two little metal balls, and I'm going to rub them both with like a piece of cloth or something, so that they each acquire a certain amount of charge. And for convenience sake, let's assume that they both have the same amount of charge on them. And then what I'm going to do is I'm going to tie those two metal balls together with a string, hold the string in the middle, and have them dangle downward. Does that make sense?
Mm-hmm.
Now, because the two balls have the same charge, there's going to be a Coulomb force of repulsion between the two balls. So when I hold the string in the middle, they're not going to hang straight down. They're going to push away from each other. And so what's going to happen is I'll have a string. Here's ball 1. Here's a string. Here's ball 2. And I'm holding it right here. And let's say that this string is 10 centimeters long, and they push themselves apart such that the angle between the two halves of the string is 30 degrees. Now, each of these balls has a mass of 10 grams. So far, so good? Mm-hmm. Based on that, how much charge is on each ball?
Okay.
Right, that's my goal, is to find the charge on each ball.
So each ball is 10.
So let's go back to like first principles here. Based on all this, where do I start?
Well, we already drew everything out. I think, don't we do our coordinate system now?
Well, we'll do that in a minute. That's probably our second big step. But the first thing you should do for a problem like this is a free body diagram, right? We need to figure out what forces we have in play. Because at the heart of this is a chapter 4 problem, right? This is a Newton's law problem. So what I'm going to do is, I could do it for either of the two balls, but I can get the answer with just one ball. So let's concentrate on one of the two balls. Let's just pick this one right here. Okay? Which forces are going to act on that ball?
Gravity.
Yeah, there's obviously gravity going to pull it straight down, and that's going to be the mass of the ball times g. What else we got?
Tension from the string.
Yeah, the string is going to pull it diagonally up and to the left. What else we got?
I want to say normal force, but...
So when you're identifying your forces, you always want to think about it in terms of like pushers and push-e's, right? Every force happens because of two objects interacting. Now, like if I'm looking at like the force of this pen on the table, there's a normal force on that pen because the pen is touching the table, right? Most forces have to be forces of contact, where the two objects are touching each other. And the only exception to that last semester was gravity. Gravity was what we call a field force, because the pusher, the planet Earth, and the push-e, like say you, don't have to be touching for there to be a force of gravity. Even if I'm in the air above the ground, gravity still pulls on me. But last semester, that was the only force that worked that way. Every other force, the two objects had to be in contact. Well, this semester, the Coulomb repulsion is another field force. You know, there's going to be a Coulomb repulsion because this guy is going to push on this guy even if they're not touching each other. Well, they said they had the same charge, which means they're going to repel. So this guy is being pushed. I'm going to call it FC for Coulomb force. But he's going to get pushed with a Coulomb force there. Now, as for a normal force, there would be a normal force on it if it was like touching the ground, but I'm holding it up above the ground. There's nothing else touching that ball. right? The only thing touching the ball is the string. We already got the string. So those are my only three forces. So when you're identifying your forces, Kayla, the way to think about it is ask yourself, what is it that's touching the object? Because those can exert forces. And then what field forces could there be on the object? Things like gravity or the Coulomb force. Those can be exerted whether or not the two objects are touching at all. Does that make sense?
Yes.
Cool. So there's my three forces. And that's the first step of every Newton's law problem is do a free body diagram and identify your three forces. Or your more than three forces, possibly. All right, the second step of every Newton's law problem is to choose a coordinate system and to break down each of your forces into that coordinate system. So let's just go with a regular boring coordinate system. Let's have x be positive to the right. Let's have y be positive going up. And if I was doing the Coulomb force, well, Fc is to the right only. It's not up and down at all. So it's going to have a magnitude of K Q1 times Q2, except we said they were the same, right?
Yeah.
So let's just call it Q, and they're both the same, so it'll be Q times Q, so Q squared over R squared. And Q is what we're solving for. It's to the right, so that's the positive x direction, so it's I hat, but there's no j hat component. So there's my vector components for my Coulomb repulsion right there. So far, so good? You with me there?
Mm-hmm.
Now, for the weight. The weight is straight downward, so it's negative mg j hat. But there's no x component. So far, so good?
Yeah.
All right, now what about the tension? The tension is diagonal. It's going to have some kind of I hat and some kind of j hat component. And both of those components are going to be non-zero. In order for me to figure this out, I'm going to have to break this down into x and y parts. I'm going to draw it off to the side so it's easier to see. So here's my diagonal tension. It's got an x part that's to the left, so clearly the x part is going to be negative. It's got a y part that's upward, so clearly the y part is going to be positive. It's going to make some kind of angle, but do I know what those angles are?
No.
I don't. However, I do know that it gave me this 30-degree angle right here, right?
Mm-hmm.
And if I drop a straight line down through the middle, half of that would be 15 degrees, right?
Yep.
And what I realize is that the angle between the string and straight down should be the same as the angle between the tension and straight down. So this angle right here has to be 15 degrees. Does that make sense?
Yes.
Once I've got that, I have this thing cracked. Notice the x component is the opposite side of the triangle. So this will be whatever my total tension is times not the cosine, but the sine of 15 degrees. That's weird. Normally the x component is going to come from the cosine, but because of the angle that I know, I'm actually going to get it from the sine this time. And for the y component, that's the adjacent side of the triangle, I'm going to get the y component from the cosine. So far, so good? Super easy?
Mm-hmm.
All right. So that's the second step of every Newton's law problem. We choose a coordinate system and we break all the forces in that free body diagram down into their x and their y components. What's the third step of every Newton's law problem ever? I keep pounding the table and bringing myself out of focus. This is terrible.
Generating an equation.
Yeah. Specifically, I'm going to use Newton's second law, which is the one thing that I expect you to know to the dying day of your life.
F equals ma.
F equals m freaking a. But that means the F is not just any F, it's the sum of the forces. And when you add forces, you have to add them by components. So I'm going to get two equations. The first I'm going to get from the x direction. So in the x direction, I've got two forces, this force and this force. So this plus this, so k q squared over r squared minus t sine of 15 equals the mass of this thing times the acceleration of this thing in the x direction. What's the acceleration of this thing in the x direction going to be, though?
Say that again.
So we know this is going to be f, this is the f, equals ma in the x direction. But what's the acceleration going to be in the x direction?
Isn't it going to be, well, it's going to be going negative since it's going in the opposite direction of how the x coordinate is.
Hang on, back up. Think about this in terms of common sense. What's happening? I've got these little balls, right? I'm holding the string, and they're just sitting there.
Mm-hmm. So it's going to be 0.
Yes.
Since they're not moving.
This is a static equilibrium problem. All the acceleration's got to be 0. So once I realize that, there's my equation. Now, what about my other equation? Well, in the y direction, I got to have 0 acceleration there also. So this plus this, so I'm going to write it t cosine 15 minus mg also equals 0. So now I have two equations and multiple unknowns. At this point, all the hard part is basically done. All we got to do now for step 4 is solve for whatever we want to solve. What am I trying to solve for again?
The force. Well, what is the what's it called? We're looking for the force. Well, not the, is it the force? The force, why are they pushing, like, what is the, oh, we're just looking for the charge. We're not looking for how far they're pushing apart, their force that they're pushing apart from.
Nope. The thing we were looking for is the charge. And the reason I make a big deal out of that is because it's super easy to kind of get lost, right? We spent all this time breaking stuff down, and we would have broken it down this exact same way regardless of what we were solving for, right? So sometimes you have all these like letters and stuff here, and sometimes students will kind of lose track of the big picture. So it helps to every once in a while pause and ask yourself, what the heck am I trying to do again? Because it's super easy to get kind of mixed up. So we're looking for Q. Q is the thing that I want. That's the charge. All this other garbage, I don't care about. So either there's a number for it already, or if there's not, I need to find a way to get rid of it. So, in this list of stuff, do I have a number for K?
Yes.
Awesome. Do I have a number for Q? No, we're solving for it. Do I have a number for R?
No.
Don't. So I'm going to have to do something to figure out the number for R before I can solve this. All right, do I have a number for T?
No.
Yeah. So don't know R, don't know T. That's a problem. Do I have a number for M?
Yes.
Awesome. So M is just a number. That's no big deal. G. That's 9.8. That's no big deal. So the trouble spots here is I got to find some way to get rid of R, or to get rid of T and to get rid of R. And if I do both of those things, I got nothing but numbers and Q, and I can solve for Q. Well, R is going to be a thing we'll have to think about here in a minute. But T is easy because I notice that T appears in both of my equations, right?
Mm-hmm.
The fact that T appears twice means I can use one equation to get rid of T in the other equation. So that's how I'm going to solve the problem of what do I do with T. So let's go over this equation over here, right? If I get T by itself in this equation, I'd add this to both sides, and then I'd divide by the cosine of 15. So T is going to equal mg divided by the cosine of 15. So far, so good?
Yes.
Awesome. Let's take this expression for T, plug it in over here. Now T is eliminated. We don't care about T anymore. So now, my equation is KQ squared over R squared minus And I've got t, which is mg over cosine 15 times the sine of 15 equals 0. And of course, I can make that prettier because I recognize that sine of 15 over cosine of 15, that's the same as a tangent. So if I wanted to, I could write it kq squared over r squared minus mg tan 15 is equal to k. So far, so good?
Mm-hmm.
All right. So I've still got this problem of I don't know r. If I solve this for q to q by itself, I'd move this over. I'd multiply by r squared, divide by k squared. So I'd have mg tan 15 times r squared divided by k. And of course, that means that q equals the square root of r squared mg tan 15 over k. And everything in here I have a number for except for r. Right? I need r to get out of here somehow. So, let's go back to my original diagram. How the heck am I going to figure out r?
Well, since you already cut the 30 in half, can't you just find that out? Because it makes a triangle when you cut it. Just makes a smaller triangle when you cut it in half.
And that's exactly what I'm doing. Because on my picture, r is the distance from this guy to this guy, right? Here is r, right, on my picture. And what I realize is that right here, this is a triangle. And I know that this side of the triangle is 10 centimeters. And this over here is not r, but it's half of r.
Mm-hmm.
And that angle up there is 15 degrees. So if I go off to the side, I've got a triangle where this is half of r, that's 15, and this distance here is 10 centimeters. And at that point, I got two sides and an angle. I'm good to go. So if I do opposite over hypotenuse, that's the sine, right?
Yes.
So the sine of 15 degrees has to equal the opposite side, which is half of r, over the hypotenuse, which is 10 centimeters or 0.1 meters. So far, so good?
Mm-hmm.
And this is a whole other equation, which I can now solve for r. So if I take 0.1 on both sides, so 0.1 times the sine of 15, that's going to equal half of r. So then if I double that, 0.2 times the sine of 15 is equal to r. And I can take that expression and plug that up in there. So now we are super, super good to go. So what is r? So 0.2 times the sine of 15. So r is 0.05. 0.05176. Notice I'm keeping extra sig figs. I don't want to round too much, so that's that squared. Times m. What is m?
10.
No.
I thought you just said, oh, but it's in grams.
Yes. I don't want to use grams because the SI unit of mass is the kilogram. So I'm going to divide that by 1,000 and not use 10, but 0.01. That's a very, very common mistake. G is 9.8. So we're going to crunch a bunch of numbers here. So r squared, crap, not square rooted. So I'm getting 8.85 times 10 to the minus 8. Which is about 88 nanocoulombs.
Yeah, that's what I got.
So that's the whole shebang, right? The idea is, you know, at the heart of it, this is just a chapter 4 problem, right? The only thing that was different that we hadn't done before was we've introduced a new kind of force, and all we had to do is use the Coulomb force law to find how big that force was. But all the rest of this is just chapter 4 stuff from last semester. So everything you've learned before, it still works. It's just you're using it in a new context that you hadn't used it before. Does that make sense?
Yeah, I see it.
So this should have you pretty well set up to do the first batch of homeworks, and I have them due at the end of the weekend. That's going to put us about halfway through chapter 18. The other half of chapter 18, we're going to introduce something called the electric field, which is just another way of thinking about where the electric, or where this Coulomb force comes from. The idea of how is it that this guy over here can exert a force on this guy over here when they're not touching? And the way we're going to model it is we're going to imagine that everything that has charge creates this like weird sort of disturbance that's invisible, you can't see it. And what's going to happen is other charged objects are interacting with that weird disturbance. And that's what the electric field is. So I'll probably post a second video to make up for like the classroom missed yesterday sometime this weekend, and that should set you up to do the remainder of the chapter 18 homeworks that are due early next week. So take a crack at those chapter 18 homeworks, that first batch, and hopefully you'll be all right. Tomorrow I'll post the first lab assignment. I forget what time I have the labs meetings for this, but if you're more than welcome to show up for that. It's certainly helpful, and especially because there's group work. It'll help you to set up groups. But we're going to do labs pretty much the same way we did last semester, where I'll break you guys into groups. This is a small enough class; you probably won't even need to break into groups. But that's how that'll work. So you can do them asynchronously if you want, but I'll dedicate some time tomorrow for you guys to work on those things. So far, so good? You feel like you know what you're doing?
Yeah, I'm probably just gonna, once the video posts, I'm probably just gonna go back and review it real quick and write down some notes that you're sending.
Gotcha. All right. Well, I will see you tomorrow or next week or whatever, and have a good day.
Bye. You too.